Hello all, welcome to my channel. So I am here to describe you about semiconductors. Now, as we have discussed in the last class that the semiconductor's resistivity or the conductivity lies between insulators and conductors. So now I would be distinguish between semiconductors, like how they are different and how they basically form new type of semiconductor. So in this, the first, the first division on the basis of purity is intrinsic, and the another one is extrinsic. So in intrinsic semiconductors, they are extremely pure form, which is known as intrinsic semiconductor. That means they are pure form of semiconductor. We are not adding any impurity to it. So the semiconductors which are pure is known as intrinsic semiconductor. Example, you can take it as silicon. We have germanium as well. Now we have another one which is extrinsic. That means it is the opposite of intrinsic. That means they are the impure semiconductors. They have some impurities in it. Now, what I mean by impurities is that they have been doped with some better impurities to make them more conductive and to have their performance much better than the intrinsic one. They are made so. Now, extrinsic is divided into N-type and P-type. Now, I would be talking about N-type first. So let us first discuss about N-type semiconductor. Now remember that N-type semiconductor is the one which is the doped one. So in this case, we add a pentavalent impurity to pure semiconductor. So a pentavalent impurity has been added to a pure semiconductor. Now, when we talk about pentavalent impurity, that means we would be adding an element which has 5 valence electrons. So in this case, let us draw a simple diagram of germanium first. If I make all the elements germanium here, then it will be a pure semiconductor. But as of now, I want to tell you about N-type semiconductor, so I would be keeping a gap here in between the elements. So suppose we have a germanium crystal. So I want to add a pentavalent impurity. So I would be taking the arsenic. Arsenic is one example of pentavalent impurity. So I would be adding a arsenic here. So as I earlier told you that it should be a pentavalent impurity. That means it should have 5 valence electrons. So let us add first one, second one, third one, fourth one. So the leftover one will be somewhere in between the crystal itself. So this is my free electron present in the N-type. Now, the fifth valence electron of arsenic atom, as you can see, does not find any place in covalent bonds and is thus free here, free to move inside a crystal. Now, these impurities which produce N-type semiconductors are known as donor impurities. So these are also known as donor impurities because they donate or provide free electrons to the semiconductor. So these are known as donor impurities. Remember this. Now I would be drawing the energy band gap for the n-type. So let us make conduction band. Let us make valence band. Now we have a free electron. So if we have a free electron, that means it must be here near the conduction band because it is a donor energy level. Now electrons are almost here near the conduction band. So as you can see, this is my donor energy level, and the difference between conduction band and the donor energy level is now reduced to so less that they can conduct electrons easily to from donor energy level to conduction band. Now we need to apply less amount of electric field near n-type semiconductor. They will conduct very easily because the energy level has been raised to the conduction band. So therefore we can say that the conductivity of n-type is marked significantly, and as you can see that we have added arsenic. That means this is not a single element. We have added multiple atoms of arsenic in it. Therefore, we have many free electrons in the one crystal. In one crystal, we have many free electrons. That doesn't mean that I have added only one atom to the germanium crystal. That won't help us to have an n-type semiconductor. We need to have we need to add many atoms of arsenic to the germanium crystal to make it conductive or to make it better. So that's how we make it better. So my next topic is p-type semiconductor. And remember, in this we have more number of electrons than holes. Now, you will be very clear when I do p-type semiconductor what holes are. So the second topic is p-type semiconductor. So in p-type semiconductor, when a small amount of trivalent impurity is added to pure semiconductor, it is called a p-type semiconductor. Now, I would be drawing the same structure of germanium. Again, I would be keeping the middle one empty to show you how we need to add a pentavalent impurity. Now the outermost ones are almost complete, the germanium atoms. Now I would be adding a trivalent impurity here. So the trivalent impurity is gallium. It has 3 valence electrons, or even we can use indium. It again has 3 valence electrons. So let us add gallium to it. So gallium has been added. Now we have 3 valence electrons. So it can therefore make 3 covalent bonds with respect to germanium. Now, as you can see, the fourth covalent bond is empty here. And I would be denoting holes as this and electrons as the complete circle. So, this will be considered as a hole. Now, again, I need to repeat that I am not adding one gallium atom here. I am adding hundreds or millions of gallium atoms into the germanium crystal. That means we have many holes inside this crystal, the p-type semiconductor. Now, this type of impurity is also known as acceptor impurities because this can accept multiple electrons. So this is also known as acceptor impurities, because the holes created can accept the electrons inside this hole. Now, the next thing, the fourth bond here you can see is incomplete, being short of one electron. Now this missing electron is called a hole. Therefore, for each gallium added, one hole is created, and a small amount of gallium provides million of holes. That means we have now NH greater than Ne. That means number of holes is greater than number of electrons in p-type semiconductor. Now the electrons from the valence band here. Now let us draw the energy band graph. So it will be a conduction band here, a valence band here. The valence band is completely filled. Now as you know that here we have a acceptor impurities. So it is actually very near to the conduction band, and we need to draw holes here, many holes here. Now, how this has been created is because of acceptor impurities. Now, how it will help us to have better conductivity is because now if we apply this small electric field so that electrons jump from here to reach these holes, then these electrons will be carried to the conduction band. Now this will be very easier for us to conduct electricity from p-type semiconductors. So that's the difference between N-type semiconductor and P-type semiconductor. In N-type, remember that we need to add a pentavalent impurity, and P-type, remember that we need to add a trivalent impurity. And one more thing is important, that in N-type we have number of electrons more as compared to the number of holes, and in p-type remember that we are giving uh, we have more number of holes than number of electrons. So that's the today's lecture. I will continue with the junction formation, that is p-n junction. So we'll be there.